Bismillahirrahmanirrahim. We have two inequalities. In the first one, x and y are non-negative. Both are less than pi over 2. Their product is less than or equal to 1. We need to show that sine of xy is greater than or equal to the product of sine x and sine y. The first derivative of sine x is cosine x. If we differentiate with respect to x again, we get minus sine x. This is less than 0 for every x in the open interval between 0 and pi over 2. Thus, on this interval, sine x is a concave function. We also have that sine x is less than or equal to x for every x greater than or equal to 0. If x is greater than or equal to 1, this inequality is obvious because sine x is less than or equal to 1. If x is in the range between 0 and 1, we define the function g of x equal to x minus sine x. G of 0 is equal to 0. The first derivative of this function with respect to x is 1 minus cosine x. This is positive if x is greater than 0. Over this interval, the function is increasing, so g of x is greater than or equal to g of 0, which is equal to 0. X is greater than or equal to sine x. What is the implication of this constraint? X and y cannot both be above 1. If x is greater than or equal to 1, y is greater than or equal to 1, this implies that the product is greater than 1. It is given that the product is less than or equal to 1, so either x or y is in the interval from 0 to 1. Without loss of generality, assume that x is between 0 and 1. Sine xy is equal to sine x times y plus 1 minus x times 0. Because x is between 0 and 1, this is a convex combination of 0 and y. Because the sine function is concave, on this interval, this sine is greater than or equal to x sine y plus 1 minus x sine 0. This is 0, so sine xy is greater than or equal to x times sine y. But x is greater than or equal to sine x, so x sine y is greater than or equal to sine x sine y. We get the inequality that sine xy is greater than or equal to sine x sine y. The second inequality is concerned with non-negative x and non-negative y. We need to show that the absolute value of the hyperbolic cosine of x minus the hyperbolic cosine of y is greater than or equal to the absolute value of x minus y times the square root of the hyperbolic sine of x times the hyperbolic sine of y. Note that if x is 0 or y is 0, then the right-hand side is equal to 0. On the left-hand side, we have an absolute value, which is always greater than or equal to 0. If either x or y is 0, then this inequality is automatically satisfied. We can focus now on the case in which both x and y are strictly positive. Suppose that you have a function h of x, and it is convex on a subset of the set of real numbers. Then for every a and b in the domain D, we have that h of a is greater than or equal to h of b, plus the first derivative of function h, assuming that it is differentiable, evaluated at b times a minus b. The first derivative of the hyperbolic sine of x is the hyperbolic cosine of x. If we differentiate again, we get the hyperbolic sine of x, which is positive when x is positive. The hyperbolic sine function is convex. When a and b are positive, we have that the hyperbolic sine of a is greater than or equal to the hyperbolic sine of b plus the hyperbolic cosine of b times a minus b. On the left-hand side of the desired inequality, we have the absolute value of the hyperbolic cosine of x minus the hyperbolic cosine of y. Let's assume, without loss of generality, that x is greater than y is greater than 0. The hyperbolic cosine of x minus the hyperbolic cosine of y can be written as the integral of the hyperbolic sine of t. T is between y and x. Let's employ this inequality. So we have the hyperbolic sine of t, and for b, I will choose x plus y over 2. The arithmetic mean of x and y. We have here plus the hyperbolic cosine of x plus y over 2. Then we have t minus the average. This is not a function of t. We can take it outside the integration, and when we integrate, we get x minus y. Then we have the hyperbolic cosine of x plus y over 2, integral t from y to x, t minus x plus y over 2. This integral is 0. It is equal to 1/2 x squared minus 1/2 y squared minus 1/2 x plus y times x minus y, and this is 0. Our current result is that the hyperbolic cosine of x minus the hyperbolic cosine of y is greater than or equal to x minus y times the hyperbolic sine of x plus y over 2. Let's have another look at the desired inequality. We have here the square root of the product of the hyperbolic sine of x and the hyperbolic sine of y. We are done if we can show that the hyperbolic sine of x plus y over 2 is greater than or equal to the square root. Let's investigate the square of the hyperbolic sine of x plus y over 2 minus the product of the hyperbolic sine of x and the hyperbolic sine of y. If we show that this quantity is greater than or equal to 0, then we are done. We can rewrite this product as 1/2 the hyperbolic cosine of the sum x plus y minus the hyperbolic cosine of the difference x minus y. We also have that the hyperbolic cosine of alpha is 2 times the square of the hyperbolic cosine of alpha over 2 minus 1. Let's apply this rule here. This difference is equal to the square of the hyperbolic sine of x plus y over 2 minus 1/2. This is 2 times the square of the hyperbolic cosine of x plus y over 2 minus 1. Then we have minus 2, the square of the hyperbolic cosine of x minus y over 2 minus 1. We can simplify and write the square of the hyperbolic sine x plus y over 2 minus the square of the hyperbolic cosine of x plus y over 2 minus the square of the hyperbolic cosine of x minus y over 2. The hyperbolic cosine of beta squared minus the hyperbolic sine of beta squared is equal to 1. This means that this difference here is equal to minus 1. This quantity is equal to the square of the hyperbolic cosine of x minus y over 2 minus 1. For these real arguments, the hyperbolic cosine function is greater than or equal to 1. So this is greater than or equal to 0. This implies that the hyperbolic sine of x plus y over 2 is greater than or equal to the square root of the hyperbolic sine of x times the hyperbolic sine of y as desired.